So first of all, thank you for inviting me, Roberto, and so I'm really happy to be here today. So as you know, as maybe other people here attending know, I'm a researcher at the National Research Council of Italy. I'm a researcher now for some years, unfortunately, but my research interests are different. Maybe there are many research interests, maybe too many. I'm dealing with flood hazard zonation or maybe early warning system, landslide early warning system, but also very peculiar types of things like, as an example, atmospheric CO2 consumption due to soil and rock weathering. But okay, I also work on landslides, and today I'm here for presenting a recent work we have done and published, and that is about the exposure of the Italian railways to rapid flow-like landslides. So I'm going to start my presentation. So first of all, let me introduce some quick definition. So with the term rapid flow-like landslide, we use this kind of term to indicate rapid to extremely rapid movements that so includes debris flow and mud flow. And from our point of view, but also in a lot of research paper in the literature, we can distinguish this phenomena into two main classes. So the channelized and hill slope phenomena, or confined and unconfined phenomena. So whatever you want to call them. So the objective of the research at the time we did it was to produce a national map of railway network exposure to these rapid flow-like landslides that can be used to support a national landslide early warning system. So we are working at national scale. And so obviously this kind of research is a sort of a challenge, because for sure you can create a product, but you need to ask yourself if this product is reliable and if the performance of the product is consistent across the entire territory. So let's start with explaining the procedure. And first of all, I want to introduce the input data. Since the procedure is actually a data-driven procedure, and this is due to the fact that working at this scale, it's very hard to work to manage, as an example, geotechnical data and soil information and so on. So we decided to move towards a data-driven approach. And in our case, this was primarily based on 3 detailed training inventory or rapid flow-like landslides. We have one of them in the northern part of Italy that we call Lombardy inventory, another one that is in central Italy that we call Umbria inventory, and another one in the southern Italy that we call Sicily inventory. And together, these 3 inventory includes something like 10,000 landslides inside. I mean, information about flow-like landslides. I also want to say that we matched these inventories to portion, we heuristically matched this inventory to portion of Italy, which have similar geomorphological characteristics, because we want to train models inside this study area, these training areas, and then we want to apply this model to the remaining portion of the territory. So for doing this, we need to define which portion of the territory is similar to the portion of the territory where the inventories are. So our procedures also include the validation phase, and in our case, the validation was carried out using an independent data inventory that is completely different from the one that we used for training the models. And this inventory is including something like 23,000 landslides. It is called IFFI inventory. and it's available for the entire territory at national scale, but with differences in terms of density and quality of the product at regional level. So the last slide about the input data, what else we need for our procedure. For sure, we need the railway network map. And in our case, it's 17,000 kilometers of railways moving across Italy, and we split this network into 1 kilometer segments in order to have to produce detailed results at the level of the kilometer. And then we need for sure a digital elevation model, and in this case we used a 10 by 10 meter resolution digital elevation model available for the entire territory. So the first step of the procedure is the classification of the training landslides into channelized and hill slope landslides. In order to do this, we decided to follow a sort of objective approach, and so we intersected the slope unit boundaries that we created together with Massimiliano Alvioli in 2020 with the landslide inventory, and when a landslide was intersected by one of the boundaries of the slope unit, we consider this landslide as a channelized phenomenon, while if the entire body of the landslide is included inside the polygon of the slope unit, in such a case we consider this landslide as an hill slope movement. We made another assumption. We say that the source areas of the different, say, debris flow, mud flow, flow-like landslides, the source areas correspond to the cells within each landslide that lie above the 10 percentiles of the elevation distribution. So it is a strong assumption, but this is what we decided to do in order to be, again, more objective and avoiding personal interpretation. Within these source areas, we proceed to analyze all the pairs of value of slope angle and flow accumulation area you have for each pixels that is inside the source areas, in the way you see here, in a way that you have a sort of scatter plot in a plot of tangential tangent of slope against the flow accumulation. And later we decided to fit this flow accumulation slope pairs using different power law quantile regression curves, following the approach proposed by Reichenbach and Zimmerman in 1993, but well used after also in other paper even recently. And using power law quantile regression, we decided to create at least 6 different power law functions for the different percentile, different quantiles you see on the left side of the slide. We did this for the 3 different training inventories, so Lombardy, Umbria, and Sicily, and for the different type of phenomena, hill slope and channelized, in a way that at the end we have many different equations. But then we use these quantile regression curves to identify the slope and flow accumulation condition where the source area of a flow-like landslide is more or less probable. I mean, you see from this slide that in the red portion of the due to the way we created the quantile regression, the red portion of the plot is the portion that is including the most abundant portion of the point representing source areas in our inventory. And then you move up and down with different quantities. Exploiting this kind of classification, we were able to, let's say, classify all the remaining portion of the Italian territory and we obtain two different maps for simulating the, let's say, the possible location of source area for channelized and hill slope debris flow. For sure, this different color represents a different level of probability of being a source areas, with the red having the larger probability, the yellow the intermediate, and the blue the lowest probability. Once we have the source area, and inside the training inventory, we use this tool that is called random walk and was created by colleagues called Martin Mergili. And this model is able to simulate different, many flow paths, starting from the source area of the training landslide and moving down, following some kind of hydrologic rules. And all these path trajectories were terminated only when they exited the landslide polygon. So they were let go, they were let run until they reached the boundary of the landslide polygon. In this way, we were able to measure what is well known in literature as a reach angle, and we were able to record a large amount of reach angle for the different type of landslides, and I mean channelized and hill slope, and for the different inventories, available inventories. And in this way, we were able to obtain some statistical distributions that we modeled as a Gaussian distribution. And these are the statistical distribution of the reach angle for the different type of landslide and for the different training inventories. So now we are at the step that concern the real modeling of the flow propagation, or the, let's say, estimation of flow propagation at national scale, starting from the source areas that we defined before and that have different probability of being a source areas. And so we simulated, I can say, millions of trajectories running from the source area and going down through the hill. And obviously, the number of trajectories released depends by the probability of being a source area of the source area, and the length of the trajectories depends on the reach angle values that are randomly sampled from the modeled distribution we have seen before. So combining together all these things, we were able to obtain maps of landslide susceptibility to the propagation of these flow-like landslides, and map of railway exposure. I will explain a little in a few seconds how this was obtained. But here you can see three maps. In the first one, you see a sort of you can see the map of an enlargement of a single portion of the Italian territory, where we show the susceptibility to channelized phenomena. And also you can see a map of railway exposure with the different segments that have different colors depending on the exposure level. And the same you have for the hill slope phenomena. You can see they are quite different. And also we have a combined map that, following a conservative approach, is obtained choosing the worst case scenarios for the different pixels. And so in case the channelized susceptibility is larger than the hill slope, we chosen the channelized and vice versa. So Susceptibility to flow-like landslides in this map depends on the number of trajectories that are passing through each pixel, while the railway exposure depends on the number of trajectories that are intersecting each segment. So this is why you can see different colors in the map. For sure, at this point, we are still in the phase of creating maps, and everything can be valid. But as I said before, in our approach, we also try to validate the products. And so the first things we did was to try to validate the susceptibility map. In order to do this, we use the classic approach of the rock curve, I mean, that people probably know, and we decided to analyze all these all the performance of the performance of the models at the level of the different Italian regions. This was done because in Italy the inventory that was used for the validation, that is a completely independent inventory with respect to the ones we use for training, is created by the different administrative regions. And due to this fact, the quality and the characteristics of the inventory are sometimes very, very different. So it can be very heterogeneous across the different regions. So in this plot, the colors represent the area under the rock curve values. And you see that the value range from the black color, that is an inverse performance of the model, because sometimes it happens. And then you move from yellow, that is, orange, that is poor performance, and you arrive to the green, that is a very, very outstanding performance. So here in the plot, you can see as an example that Lombardy has a very good performance, but also other Latium and other regions in Italy. Then we have the points represent the different Italian regions, so different portion of the Italian territory, and the axis X and Y represent an estimation of the density of information in terms of area density or count density of the landslide inventory we used for the validation. So what we observe is that there is no clear correlation between the density of the information we used for the validation and the performance of the susceptibility model. So it is not the number of landslide that we have in the validation dataset that is in some way affecting the quality of the performance. So in order to understand why there are regions where the model is working better, and most of all, why there are regions where the performance are bad, so we decided to go and to search in depth inside the inventory, and we discovered that in some Italian region, administrative regions, the quality of the validation inventory was very poor, is very poor, and there are, as an example, some landslides that are actually airflow or deep-seated landslides or similar landslides that are classified as flow-like landslide, rapid flow-like landslide. And for sure, we can understand that our models cannot be able to detect this kind of feature. So we discovered that probably the bad performance of our tool our procedure was mostly due to the quality of the validation inventory. But, and we are close to the end of the presentation, we still have the problem of understanding if the exposure map, I mean the map of the railway segments that we classified in terms of exposure, in terms of let's say, in some way, the probability of being involved in a flow, in a fast flow like landslides is good if this map can be considered reliable. So in order to understand this point, we decided to plot in form of an histogram the relative frequency of the railway segment in different exposure classes. So in this plot, in the x-axis, you see different value of railway exposure, starting from 0 and arriving to 1. And there are two different histograms. The first one is the histogram of the exposure value of all the railway segments in Italy. And for sure, we excluded the flat areas because this would be too much trivial. So we are only talking about railways that are inside valleys or close to mountains or hills. Then we have another histogram that is the gray one, that is representing the relative frequency of the railway segment where we have documented, where we know that for sure in the past some interaction between the railway and the rapid flow like landslide occurred. So we know that these are segments where phenomena may create some kind of problem to the railway. And as you can see, selecting only these segments, we see that the distribution is very, very skewed towards the values that are on the right side of the plot, so very close to the value 1. And this in some way indicates a sort of good classification of our exposure map. So coming to the conclusion, I can say that we can say that high quality landslide inventory, even if they are in some way compiled for very, very limited portion of the territory, as in our case for Piedmont, for Lombardy, Umbria, and Sicily, can be used for training models that can predict the propensity of the territory to be involved in a rapid flow like landslides, also over large areas at national scale. The source areas and the travel distance angle of the hill slope and channelized rapid flow like landslides are generally different and should not be handled and simulated together, but must be treated separately and then probably merged together. I can also say that in most Italian regions, the performance invalidation of the runout susceptibility maps is at least acceptable. I mean, in the most part of the Italian administrative regions. And where the performance is low, frequently there is an inconsistency in the quality of the inventory. And so this creates the problem of the poor performance. Lastly, we have something like 15% of the Italian railway network that is highly exposed to this kind of phenomenon. So if you want to have more information about the paper, here you can see the paper, the reference to the paper that was published this year. And also I want to highlight that with colleagues from Spain and Natural Resources of Canada, we are working on another paper that was recently submitted and is currently under revision. So thank you very much.